together a few slides talking about some of the propagation differences between our favorite bands, and threw in some 900 megahertz here and there as well as a comparison. A little bit about me. Systems engineer here at 7 Signal, supporting the sales team, our resellers and customers. I have been doing something with wireless LANs, designing, installing, troubleshooting here at 7 Signal, optimizing for about 30 years. So I've seen a lot of technologies come and go. As I said, this time we're going to talk about a few differences in propagation between the various bands. And I'm going to start with free space, mountaintop to mountaintop, asteroid to asteroid, that kind of thing. We pointed out or mentioned on a previous webinar that in free space there wasn't a huge amount of difference between the bands. So I plotted that 0 to 10 kilometers free space loss for 900 through 7 gigahertz. 7 gigahertz being kind of near the top of the 6E band, nice round number. And up at the top we have the basic formula for it, and there's really 3 components: the distance, the frequency, and a constant at the end that is going to change depending on the exact units that you use. I think it's obvious why distance is in there. Obviously, as the signal spreads, it has to cover a larger area, and that's an exponential function, so logs are kind of natural there. So that one makes sense, but and maybe this is one that you can talk about, Jim. Why is frequency in there? I mean, it shouldn't matter, right? Photons don't get tired depending on their frequency or anything like that. So why have we got frequency in there?
Yeah, it's a good question, and by being in there, it has an effect immediately, right at the transmitter too. It's not.
Oh yeah.
It's not what's commonly assumed, which is, well, higher frequencies just kind of degrade faster and have higher attenuation values in some materials, which actually that's not incorrect. But it's a function of radio equipment called receive aperture. So the antenna at higher frequencies, an antenna will absorb less and less power, and that's just a function of the frequency itself. So it all things equal, you will get about 6 dB lower signal between 5 gigahertz and 2.4 just because of that. Now, there's a lot of techniques to make up for that, particularly with those very high frequencies. The antennas are really tiny, particularly like 60 gigahertz. So you could have an array of 64 antennas all receiving the same signal and combining it and using DSP to make up for some of that loss. But definitely an important point that's often overlooked about receive aperture.
Yeah, and really it's also kind of a consequence of doing this at a constant gain, not having gain as part of this, because and it's easier to think of if you think of a dish type antenna, but the same gain, for the same gain, higher frequency antennas are going to be smaller. So there's actually less physical antenna there to grab energy out of the air.
Mm-hmm.
So yeah, that's something that it actually took me a while to kind of figure out why that was. But
so yeah,
I thought this was a good opportunity.
I think about aperture in terms of camera lenses, right?
Yeah.
And that's a good way to think about it. If the aperture is wide open in a lens, it gathers a lot more light. So that's like a lower frequency. If the aperture is shut down, the opening that allows light in gets smaller and smaller, and less light comes in, and higher frequency antenna systems behave like that.
Yeah, you're a photographer, so it makes sense.
Yep. Another thing that you can get from this chart is how cellular systems and other longer range wireless communication systems can operate over kilometers of distance. We think about free space path loss in the indoor Wi-Fi as being a problem because it attenuates so fast. But that's just
You're
the very
way down
beginning.
here. Yeah.
It's it follows a power law. So it attenuates really fast at first, but then it goes on for a long time at much lower signal strengths. And if you have equipment that can operate at those signal strengths, like cellular equipment can, you can get a ton of range from radio equipment.
Yeah. Well, I mean, obviously we're talking to Voyager out beyond the edge of the solar system. So
that's right. Yeah.
But yeah, I thought that was an interesting place to start. You know, the next thing I wanted to talk about was atmospheric absorption, because you've got all this air, you know, especially on these long links between you. So I wanted to talk a little bit about how much of an issue that is or isn't. I found this kind of neat graph with water vapor absorption and dry air, and a total on this. And I went through and highlighted 3 of our bands of interest, 2, 4, 5.5, and 7 gigahertz. And our left column is dB per kilometer. So if you look it up, we're at 1/100th of a dB per kilometer. So typically, it's not something that we consider for links below 10 gigahertz. You know, now I have done some 60 gigahertz links, which sit right here in this big loss peak. And that makes 60 gigahertz super short range. We were doing like links across parking lots, kind of things. But it means you can reuse the channels like crazy, and you can get crazy high bandwidths. In fact, there is a Wi-Fi standard for 60 gigahertz, which I don't remember the name of, Jim.
Yeah, 802.11ay, Wi-Fi Halo. No, sorry, it's not Halo. It's ATY gig. I think it was how it was branded. But yeah, you'll see some of the AP vendors have 60 gigahertz point-to-point APs for that.
Yeah, they're awesome for short haul stuff. And you know, 60 gig always seemed like a good place for stuff like VR displays, heads up displays kind of thing. But I don't know if anybody's actually using 60 gig for that, but it seems like a good application to me anyway. Moving on, some common building materials. And I did a lot of reading about this, and really, there's a lot of information out there that's tremendously conflicting. Either there's graphs like the one on the left that really don't, you know, indicate where they were sampling, you know, or on the right where they do, and the samples are so far apart in frequency that, you know, you have to wonder about the curves between them. And what I found is everybody kind of agrees concrete sucks up a lot of signal, but beyond that, there's an amazing amount of variation in opinions, let's say. And I dug around a little bit, and there kind of seemed to be a couple of things driving that. Everybody's doing the test a little differently. Although Ekahau has some nice information on suggestions on how to actually do live testing on walls as part of designs. And then there's a lot of variability in the tested materials, and we can see that on that left. I mean, we've got, you know, plasterboard, wood, ceiling board, floorboard. You know, we really don't know what those are. You know, what materials they were testing. But I think that kind of maybe the takeaway is that our 7 gig which is right here, Wi-Fi 6E, really looks a lot like the 5 gig, but a little bit more so. The transition isn't nearly as big as it was from 900 to 2.4. And I think, I started doing a lot of these in 900. So 2.4 felt really, really attenuated when we moved to it. And kind of the same thing when we moved to 5 gig, is it felt very attenuated by walls and things compared to 2.4. And the 6E, 6 gigahertz, 7 gigahertz isn't really that much different. Any thoughts on all of that, Jim? I know I talked quite a bit.
Yeah, you make a good point about, well, what exactly are the details of each of these materials? I mean, concrete could be very thick, it could be thin. Concrete has a lot more water content when it's first poured than after it's cured for a couple of years, and that changes its behavior.
It really does. And I found, like I said, a lot of material that I didn't include. And one of them, I found somebody that had tested new concrete against 40-year-old concrete, and he did find quite a bit of difference. And of course, I think we've all seen that ourselves, that fresh concrete just soaks up signal.
Mm-hmm. Yeah, for sure. And so I think it's important to measure the stuff that you're working with. Glass as well. I've done Wi-Fi in buildings with solar tinting in the glass to reflect UV energy for energy savings, and some of that stuff, you could have 30 dB of attenuation from that, which is really remarkable. It's more than the exterior walls in some buildings.
Yeah,
So,
glass is one of those super unpredictable materials. The composition just varies so much, and the tintings and coatings make a huge difference.
Randy in the chat saying even wood has variable water content.
Yeah,
Of course it does. Yeah.
wildly so. And common things like sheetrock, there's the kind of the rugged duty wallboard that's got fiber reinforcement and things in it. And it's much denser than your regular everyday drywall. So yeah, I think the answer has to be that if you want a really precise design, you need to go out and do some measuring. And I don't think really that's a real controversial statement or anything. I came across this graph. It wasn't something I was going to include until I noticed this scale on it, and it's dB per micron for some conductive materials. And just to give you a sense of scale, basic printer paper is 75 to 100 microns, and they're talking, 5 or 10 dB per micron here. So yeah, I think it's you're not shooting through conductive materials is what this comes down to.
Yeah. Microns are pretty small. So
Yeah.
yeah, that's a lot.
I actually went on McMaster Car. It's a material supplier, and looked to see what the thinnest metal foil they had. And I want to say that it was 0.005 of an inch. And what is that in microns? 50 microns, something like that. I don't remember, but it's crazy. Just how attenuating metal foils are. I even had a little experience with that. I had a system that was interfering with Verizon. I was radiating right in the middle of their LTE downlink channel, and they were a little upset. They showed up with a spectrum analyzer, pointed at my box, and got a big spike. So yeah. And as a quick test, I ran down to the store on the corner and grabbed a roll of aluminum foil and just wrapped up all my equipment in aluminum foil and retested. And it pretty much shut it down. So yeah. we ended up going with metal enclosures and putting traps on everything and bandpass filters. But yeah, it makes a big difference if it's conductive.
Also, if you're making a hat to keep harmful radio waves out of your brain, then copper is the material to use.
Oh yeah, definitely.
Not
And if you
tin,
can't
go
swing
with
the price
copper.
for copper, have to go with aluminum.
Yeah.
Although, if you're worried about magnetic fields, iron might be the way to go.
Oh yeah, of course, magnetic
Yeah.
fields.
All right. Our next topic is reflection. And I was originally going to try to do, one of these kind of things, absorption at different frequencies for refraction or for reflection. But I found this. And I'm going to have to kind of, give a little tip of the hat to these guys for their little paper, Laboratory Study of Magnetic Wave Reflectivity of Certain Materials. And they did a number of materials. This is wallboard, gypsum wallboard. And they shot radio waves at it between 2 and 3 gigahertz, so at least part of the band that we're interested in, and measured the signal at different angles. The bottom here, the negative 70-ish, is basically the reflection off of their anechoic chamber. And then the peaks are reflections, back from the material. And I had always known from doing site surveys that getting through walls at about 45 degrees was really tough, and I had always thought that it was some sort of absorption issue. And then I saw this, and this graph was kind of a revelation to me. At 45 degrees in this kind of 2 to 3 gigahertz band, it's bouncing back about 30 dB of signal. So it isn't absorbing all that signal that I was finding the dead spots at 45. It's bouncing it back. And like I said, this is maybe slightly off of what I was going to talk about, but it was such a revelation to me that I wanted to include that. What do you think, Jim?
Yeah, that's really interesting. I think I learned about kind of wall absorptions and MIMO and how it takes advantage of reflections kind of in different chapters of learning about enterprise Wi-Fi, and really it, particularly with drywall, just thinking about it, well, it's 2 or 3 dB of absorption, and that's all you have to think about. Plus, if it's indoor, there's multipath. Well, if this is the most common building material we're encountering, it's got to be the source of some of that reflection, right? It is a surprising amount, though, for sure.
I was stunned. I mean, I was thinking that it was going to be single digit. I really was. And in a lot of places it is, right? There's all these peaks and valleys, which I had never noticed doing site surveys, but I had noticed that 45 degrees was hard to shoot through walls at. And yeah, for sure. So like I said, I thought that's worth webinar to me, because I understand something that I didn't understand really before. Like Jim said, I knew it was there. Obviously, MIMO works because it's there. I just had no idea the magnitude. That was stunning. And I looked at the paper, and the references down there. You can go look at it. It seems pretty well done. It's kind of real science. Kind of last major topic whenever we're talking about these is refraction, and you've got to do the pencil in the glass of water image if you're going to talk about it. And really what we're talking about with refraction is that whenever electromagnetic wave or any wave phenomenon moves into a medium with a different velocity of propagation, the frequency isn't going to change, so the wavelength has to, and that forces it to bend. So you get this effect like we see down here in the in the corner as you move in and out of different media with different velocities of propagation. And how that really matters in radio is usually outdoors, where, you know, if we take the Earth here, our green quarter sphere, in a straight line, the radio path through the atmosphere actually follows something a lot closer to the blue line. It will curve a bit because the atmosphere has an uneven velocity of propagation. Radio propagates a little bit faster higher in the atmosphere and causes it to bend. It's a big deal for things like radar operators because they are trying to exactly position something. And a huge difference for the military, right, is something over the horizon from their radar or not. So yeah, that can be a big one. Not usually, I think, much of an indoor concern, at least not actively. It's obviously going on. I could not find much information about the difference of refraction by frequency at radio frequencies. Obviously, it's an issue at light because we have rainbows, and that's a difference of the refractive index by frequency, right? And actually, that sort of prompted the Pink Floyd trivia question. But I don't know, Jim, do you ever really think about refraction in any context other than long haul?
No, just for outdoor stuff, and a lot more often, you know, when I'm tinkering with ham radio stuff than when I'm thinking about indoor Wi-Fi.
Yeah, well, ham radio, you also get those really low frequencies, so ionosphere and things like that start to matter.
Right. Yeah.
Yeah. Maybe a little moon bounce.
Absolutely.
All right. So a couple last slides, you know, just sort of a sum up on some point to point. And really it's dominated by free space path loss. That's by far the huge factor. We know there's not much air absorption. And then, you know, we don't talk about point to point much, but there are a thing called a Fresnel zone, and it has to do with what the radio waves are going to interact with in their path, and how far out of the path something needs to be for it to not interact. So essentially, if you keep your path clear of obstructions in an outdoor, the reflection and absorption by other things are a minor concern. But where you are closer to the ground or closer to the objects, reflection can be a really big deal. You know, there's always these stories, you know, shooting over a tidal body of water and the link fades, you know, every day at high tide because the multipath changes, those kind of things. But really, for the most part with point to point, it's all about free space path loss. What do you think, Jim?
Yeah, for sure. Yeah, and the one thing about the Fresnel zone is, you know, it's something to think about, particularly if you have trees or things that are, you know, you might have direct line of sight, but if trees are kind of creeping into that, you can start having issues.
You absolutely can.
Yeah.
I had an engineer that worked for me, and he had the visual sight test and the truck test for links. And for short links, it kind of works. And it was, if you have visual line of sight and there is enough room to drive a big truck right down the middle of the beam, you're okay. And if not, you need to do the math.
Yeah,
so
that's a good rule of thumb.
Worked pretty well. And then I plotted an RSSI versus distance, and I figured 10 dB of gain on the transmit and receive is a very kind of modest, you know, size of your hand sort of antenna. And it's funny, the first time I did this chart, I was thinking 50 milliwatts and plugged in 50 dB in. I'm like, wow, this range seems really good.
That's cellular power at those big towers.
Yeah, hundreds or what is that, thousands of watts. So yeah, range was really good at 50 dBm. And then indoor, I found this office that looks like it might have some glass that we don't know what's made out of, and yeah, what are those walls made out of? And indoor, really, in a lot of ways, is a lot more complicated than the outdoor, because not only do you have that free space loss that we know is vicious in those first few meters, all kinds of construction materials. What is that glass? What are those round things? Is that styrofoam or is that something else? But we don't have to worry at all about absorption by atmosphere. That's not even an issue outdoors. And refraction, yeah, it's going on. Mostly, we don't care. And that's all I have. I hope it was interesting.
Thanks, Mike. Yeah, we've had a great audience today too. A lot of people here and a lot of participation in the chat and in the Q&A. And if anybody has additional questions, drop them in the Q&A. Hey, Mike, could you bring up that first slide about free space path loss, FSPL, we'll say. Got a question from an anonymous attendee.
Uh-oh.
Yeah, they want to know, oh boy, what does the last part of the equation in the slide represent, the 4/c? I think that's 4 times pi over the speed of light. Is that right?
Yeah, it is. And I think in this equation, it's going to be in meters per second. I didn't put the units in for it. It's going to change depending on the distance unit, the frequency units, whether they're metric or customary units. And it's going to depend on whether it's meters or kilometers and gigahertz or megahertz. But it's 4 pi over the speed of light.
Yeah. Awesome to hear our attendees are crunching the numbers here on free space path loss. So you won't find this exact effect indoors, of course. So but in a vacuum, this is what you would discover.
Yeah, it's really close from mountaintop to mountaintop kind of shots. I used to do a lot of point to points. And if you do it carefully, usually you can get within 2 or 3 dB of the predicted signal strength if you're using good, well-calibrated equipment.
Yeah. Plus or minus 3 dB is pretty good.
I do remember one point to point that I'd set up. We set up a big array on top of a building, had to crane the mast up and stuff. And I set up for like a really quick test a couple of miles away. We were within a few dB of predicted signal strengths. I'm like, this is great, we're good. And then we kind of buttoned it up. We weatherproofed everything and dressed out all the cabling and stuff, and went back and started setting up my remote sites. And I was like 25 dB down from the prediction. What is going on here? And I'd swap cables and antennas, and I started doing dumb stuff like ungrounding because that was the change I had made. And eventually, after a few days, we discovered the polarization stickers on the client antennas were flipped 90 degrees. So that was upsetting. But from those point-to-point links, you can know what your signal strength should be. And if it's not, something's wrong.
Question from Pierre. Do you have any details about human body absorption in heavily populated environments like conferences, etc.? Would 2.4 gigahertz make sense in such environments versus 5 gigahertz?
I don't have any direct data, but I have some experience. We have a lot of our Sapphire Eye product in sporting venues. And they have sort of that, sometimes they're very empty and sometimes they're very full effect. And it's very clear if you look at signal strength on the access points on an empty versus a full building, that there is a lot of loss. I've seen, 6 and 8 dB change in signal strengths just between empty and full buildings. And I have to assume that that's mostly just the people soaking up signal. Oh, and the 2.4 thing, the problem with 2.4 in those big venues, or a problem with 2.4 in those big venues, is everybody's carrying around at least one Wi-Fi device just about nowadays, and they're all probing all the time. And they're probing at 1 megabit. And 2.4 access points are going to hear that a long way off and respond. So what we see frequently in those dense venues, sporting venues, music halls, that sort of thing, is that 2.4 is really just wiped out by management traffic. It's all probe responses in 2.4. So I guess you kind of have to have it on for those few devices that aren't going to connect on 5, but 2.4 in a dense environment is brutal.
Yeah, I would try and avoid it completely. It's the probing behavior, but now it's also all the Bluetooth devices that people are carrying
Yeah, it doesn't
around.
help either.
It's watches, it's AirPods, it's all these other things, and they will start chewing up the band as well. So it seems more common in those large public venues just to go 5 gigahertz only.
Yeah, I think if you're going to turn on 2.4, you need to turn it on a very small subset of access points.
Yeah. So here's a question. Never really thought about this, but any idea how to constructively use refractions indoors? Maybe for guiding waves to achieve line of sight like effect around bends? That would be pretty amazing if you had. Yeah, I think the problem is we just don't have, control over the physical environment to kind of try to build those effects into the construction of a building. It might look kind of strange.
And we saw on the here that the reflection aspect of at least sheetrock is going to be a big part of that. So you're probably bouncing more than you're refracting on those. And I surely don't have any information on refraction of sheetrock or something like that. On the other hand, I think you can absolutely use those 45-degree bounces to shoot signal around corners. I don't see any reason that wouldn't work.
Definitely. Yeah, and the nicer predictive modeling software will try to factor that into some effect. So if you're moving an AP around and can see the live results of that, you can see if there are areas where you have some constructive gain from reflection, for example, where you want to put it. So
yeah, but
interesting question.
Stunningly large effect. All right.
Here's a question from Marcus, who wants to know, from your experience when designing on 5 gigahertz, will it work for 6 gigahertz as well? Very good question, Marcus. I guess that depends on how well you want it to work, but my answer is probably not. It won't work as well for 6 gigahertz, and it's worth probably making some design changes and slightly increasing your AP density to get the right coverage with 6 gigahertz.
Yeah, I think that's the case. And really for AX in general, 6 as well as 6A, I think there's a good case for higher density, both because of the efficiency improvements in 6, but even more so because we do have those higher modulation rates available, and you need more signal to hit those higher modulation rates.
Yeah. Yeah. And the other thing, a special consideration with 6 gigahertz in the US is that clients have a transmit power limitation that's 6 decibels below APs, at least when they're using low power indoors access points. So you got to be a little more sensitive to uplink performance with 6 gigahertz, and that's also one reason why a redesign might be a good idea. Forrest has a follow-on question from our discussion around management traffic, and he says, so is there significantly less management traffic in 5 gigahertz?
There isn't less because of the protocol, but there is less because you don't have those long propagations. And remember, the client device is always going to probe at the lowest data rate for the PHY. So for 2.4, that's always going to be 1 megabit. And that travels. So every AP in the freaking building responds.
You also have the effect in 5 gigahertz of having maybe 25 channels that probing
channels,
will be spread across. And of course, the client wants to discover on every channel, but once it finds a decent enough AP to connect to, perhaps it won't end up probing across the entire band.
Although there are a lot of clients out there that just seem to probe like mad all the time.
Oh, I know. It's been a problem that for very high density networks for a while, and something we see with our large public venue customers is tracking that probing behavior when thousands of people, tens of thousands of people all show up at once and their phones just probe at the very lowest rates. Can get ugly. One thing I will mention though is in 6 gigahertz there is less management traffic. One, because of consolidating SSIDs within a single multi-BSSID beacon, but also because of new ways of probing and limitations on how probing can be done. And in fact, most clients won't even probe in 6 gigahertz. They'll probe in 2.4 or 5 gigahertz and do what's called out-of-band discovery to find those 6 gigahertz BSSIDs in the other bands, and then associate right away in the 6 gigahertz band without a big flood of new probing traffic. So haven't made the same mistake in 6 gigahertz, which is good.
Yeah, it'll be nice whenever we get a lot more 6 gig rollout. I think it's going to make a big difference, especially with so many companies moving to either exclusively wireless connectivity or mostly wireless connectivity.
A lot of interesting questions today. Here's one from Andrew. How does wind affect signaling? I don't really know. I mean, of course, indoors, we don't think about it, but any thoughts on that outdoors, Mike?
Yeah. The issue with wind is mostly with big antennas, big dishes and big panels. And we don't use a lot of Yagis anymore, but even the long Yagi booms, the wind would twist them and change the aim is the experience that I had with the effect of wind. Not so much on the electromagnetic portion, but on the physical portion. Moving, sideways a little bit doesn't make a big difference, but if you get a twisting moment from the wind, that changes the aim of the antenna. And obviously the bigger antenna, the more, opportunity for that to happen. And the bigger the antenna, the more gain. So the more sensitive it is to aiming errors. So big antennas, yeah, it's an issue with those, but yeah, not indoors for sure.
Yeah. Yeah. And once that signal is out there in the electromagnetic spectrum, it's moving at the speed of light. So probably not something wind is going to play much of a role in.
Yeah.
Certainly though, I'm sure we have some people in the southern U.S. that have seen what hurricanes can do to antenna systems. So wind is definitely a challenge there. So anonymous.
Go
Go
ahead.
ahead, Mike.
No, I was just going to say I saw one from Robert there about Yagi above a ceiling fan. I think it was when it popped up. Yeah, that's got to be an interesting effect.
Not a wind effect, but more of a blender effect, I think.
Like the what do they call it? The stirrer in a microwave oven.
Yeah. So anonymous, I think following on our question about probing behavior and management traffic, if you
Gonna have to do a whole
disable,
webinar on that.
I think so. If you disable the lower data rate, that will improve the experience, would it not? Including playing with power output. So those are kind of different things, but probing isn't, clients just probe. They don't go and look at the required data rates or anything like that. They get on the channel and immediately start to transmit, after normal contention processes, of course, a probe, because they want to do it really fast. They've got a lot of channels to check, and they don't want the end user there sitting there waiting for the SSIDs to pop up on their laptop or phone.
Yeah.
So they don't respect what the AP declares as the minimum required data rates because they're not associated. So they don't have to. They can probe at whatever rates they want.
Yeah. And I've never seen one that probed at anything other than 1 megabit for 2.4 or 6 for 5 gig.
Yeah. I think that's my experience too.
Changing that minimum basic data rate definitely makes an improvement if you turn off those lower data rates. You can't change the probes, but you can change the probe responses and you change the beacons, and that cuts down potentially on the channel utilization by management traffic. That's actually a lot of times low-hanging fruit in dense networks. If the channel utilization is high, and a lot of that is management traffic, is to go trim those lower data rates. The traffic is all still there, but it takes less time on the air. Transmit.
Yep, for sure. Daniel sent us a message to the hosts and panelists in the chat following up about wind. I thought was worth a note. He says, wind does not affect RF at all, but very narrow beam width 60 gigahertz links with 1 to 3 degree beams will get affected. And I bet they get affected very quickly. You probably can't even, it probably happens without any visual indication the antenna's moving at all. But yeah, you got to really clamp
it's those narrow
down.
bandwidths that'll get you on the wind.
Yeah.
If it's a 45 degree bandwidth signal, it doesn't matter if your antenna tweaks a couple of degrees. If it's a 3 or 4 or 5 degree beam width, it matters a lot.
Mm-hmm. All right, maybe we'll do one last question, Heather, and then we'll wrap up. Let's go to Forrest. And I think, Mike, we do need to do a webinar on management traffic and probing, because here's another question. And Forrest is asking, if a device works on 2, 4, and 5, and it's connected to 5, is it still going to probe on 2.4 gigahertz?
Driver dependent, but probably so.
Absolutely, it will. Yeah. Yeah, it is. Like Mike said, it's driver dependent, and it's up to the client to do what it'll do. But yeah, it probably will. Even if you don't have any APs or any AP radios doing anything at all on 2.4 gigahertz, clients will still probe.
And in fact, we see that on some dense venues. We've got some education customers that have 2.4 turned off in things like big lecture halls, and we will see on the spectrum analyzer that it's just blank whenever the class is empty. Right, there's a little bit of energies for some Bluetooth way over there or something. Basically, it's empty. And then when the class fills up, it's just solid energy from band edge to band edge on 2-4. And it's all probes. It's all probes.
All right. Thanks a lot, Mike. That was a great one. And appreciate everybody coming. Over to you, Heather.
Awesome. Well, thank you, Mike. Great topic, great engagement from the audience. Thank you all for being here and being so engaged. It's always a really big treat to have that. So no 7 minutes today. Eric is on the road, but we'll welcome him back next time, and we will see you then. We're going to be right back here, same time, same place next week. So we will see you all there.